6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff at 2:13. 7.6 million pounds of thrust, and it has cleared the tower.
Prepare yourself for a world of science.
Good morning, everybody. It's Conley here with Science Nights in the morning. We have the whole crew assembled. Dr. Anirban Bhattacharjee all the way from India. We have Dr. Sean Graham in the house and Dr. Thomas Schiller as well. And today's going to be a very interesting episode. Going to be kind of talking about where our energy comes from and electromagnetism. Now, Anirban is our physicist, astronomer extraordinaire, and we're all going to be kind of discussing this topic here today. And I got a lot of questions because when I was in grade school, a little boy, I saw this picture in a coloring book of this old guy who's bald. He had long hair, kind of looked like a player, like a gigolo, you know. And he had these weird clothes on. Benjamin Franklin, yeah, that's his name. And he flew a kite.
The only person who can be bald and have long hair at the same time.
Exactly.
The 1700s mullet of the time.
For sure. But hey, he was a stylish dude, man. But anyway, he was flying this kite, and he had a key on this on the string, you know, connecting to the kite, and lightning struck it, and boom! Now he has electricity. Electricity has been made. I'm educated now.
Yeah. Well, is there anything else to talk about?
Yeah, I'm sure that's totally true. That's how electricity was invented.
He put it in a bottle and started selling it.
Right.
Yeah, $5 a pop.
Yep. Is that all factual, Anirban?
Absolutely. I mean, Benjamin Franklin is like the founding father, right? So is of United States, right? Is one of the founding fathers of the United States.
No, Bolivia.
He's one of them. Yeah.
Yes.
You can just say it's total BS.
Just jump right in. Yeah. Anytime you want, jump in here.
The experiment did happen. The experiment did happen. So it's not a key, but it's a conductive wire that was attached to the kite. And he performed that experiment. It was proposed, and it might have been conducted. We don't really know that he did conduct it or not, but he proposed the experiment, and the reason was that the idea that lightning is a form of electricity, and it was already well known from ancient Greece that electricity, or that electrostatic nature, the discharge that happens, like they knew there were sparks that would come out if you rub like fur or amber for that for against a rod, like there would be sparks, like electrostatic discharge, and they wanted to show that the lightning is also a form of that. So, and they knew that electricity in that regard could be conducted through metal pipes. So they knew that 2,000 years ago. So they wanted to prove that. So that is what the idea was, like to do that is to fly a kite, and with a metal conductive like a wire in there, and to see if that's true or not. And they
couldn't you do it with a key? What
piece of metal? So the key was basically the key. So what they did is they, instead of using a conductive rod, which is or a wire, because that would make it really heavy, what they did was they used a wet hemp string, and they attached it to a kite, and then a house key by this person called Benjamin Locksley was attached and to the kite, and they flew it.
This is so postmodern. It's so postmodern. I don't know what's true anymore.
Yeah. So
somebody named Benjamin Laughlin. Who is this guy?
Locksley.
Locksley.
Loxley. Loxley, Loxley, Benjamin Loxley.
And is he a founding father from like Tajikistan or something like that? How far down the rabbit hole are we going? Where did you get this information is my question. Is this some alternate reality on Reddit or something like that?
This is what I was reading up on the kite experiment by Benjamin Franklin.
So he proposed experiment and then people went out and did it with various materials.
Yeah, so they did it, and this experiment was also then finally the definitive proof was done in France. You conducted Benjamin Franklin, and they had this 50 feet tall iron rod. They made that and they put it out there during a lightning storm, and they extracted this. Basically, they realized this lightning would hit the the rod there. Basically, it would create sparks on that, like the tall rod.
Mm-hmm. So that's one of the first iterations of a lightning rod, like that we use today.
Yeah.
Okay.
So let's kind of start with an even more complex question here, Anirban. What is electricity, and what is a magnet?
And how do we contain it?
Okay. How do you contain
You made
it?
my really difficult question very, very complicated, Con. What is electricity?
Okay, so electricity. The name electricity comes out of the word from the word amber, right? So, amber was the Greek word for amber is called electron, and that's where you would have the static electricity really well observed. Like if you would rub it, amber, and touch it against something else, you will see sparks of electric, the discharge happening, that sparks flying, and that's what they said. And then that mysterious property, since it was derived from amber, it was called electricity because the Greek name for amber was electron, not Electron. The Greek spelling is Elektron.
Right. Yeah.
So that's where the name electricity comes out of. So.
Yep, but that's not what Thomas asked you. He asked you what it is.
So electricity is the phenomena that happens when you have electrons, which are negatively charged subatomic particles, which move from one end to another. That's when we see electricity coming into play, that we know.
Okay.
Does that answer your question, Thomas?
I think so. So what's a magnet?
Excellent question. And now magnet is basically the property of magnet. When we see magnet, the attractive property or the repulsive property or whatever it is when this electron starts spinning in a certain direction, they create an attractive force. Depending on the way they are spinning, they will either attract one set of electrons or they will repel them. So depending the way they are spinning, they will create this attractive or repulsive force. That's where the magnetism comes out of. If you take a charge and make it move, it creates magnetism.
Okay, so that comes to my third question. How can we contain it and sell it on a large scale and sell it to people on a monthly basis? How are we going to do that?
It's a good idea.
Yes, that's a very interesting question, and I do have an answer for that. So when this was happening, this question was asked not by you. You are not the first person to ask. So, one of the future Prime Minister of UK, Sir William Gladstone, very famous person, asked Faraday, "What's the use of this?" Then Faraday replied, "Why, sir? There is every probability that you will soon be able to tax it."
Oh, great!
Is that real? That's the story.
That's a real quote in a or not a real quote, or like more like an anecdote. When he was Faraday was showing like how electric current flows and how magnetism works. And I will talk about Faraday's what Faraday showed in a little bit later. But when he was doing these demonstrations, Gladstone, it seems like, asked him, like, what's the use of this? Faraday basically told him, well, I'm very sure you can, like,
You'll be able
you
to
can
tax
tax it later.
That's pretty cool, because I'm sure
Yeah.
the prime minister at the time is still like, what is he talking about? You know, it's just like this stupid little tube that's making these little sparks, and it's like, this guy's out of his mind. But Faraday is already 4 steps ahead of him. First of all, it will be useful, and third of all,
so you can tax it.
You'll be able to tax it.
Huzzah!
Wow.
No, it's just one of the fundamental questions. Like, you know, as a scientist, we are always asked, what's the point of what you're doing? What's the use?
Well, how did it get from kind of a fun little science experiment, and I'm guessing like the 1800s, 1700s, to something that we all use for everything and that you have to pay for? You know, is that the part of the history you wanted to talk about, or did you want to jump in somewhere else?
No, it's just a general. I was more interested. I wanted to give this idea that people thought static electricity or the discharge had no connection to magnetism at all. So there is this history behind which slowly was unraveled, and like people slowly found out, like little by little, like how those two things were related. So one of the things, this is this Dutch scientist, who is not a scientist actually, I should not say he's a scientist because his PhD was in philosophy, and actually in Immanuel Kant's philosophy of unity. And like Immanuel Kant basically wanted to, had this idea that nature is interconnected. So he wanted to kind of just had an idea that, well, this is electricity. We know this is electricity, and there is magnetism. Are these two things connected? So he wanted to show that if all things in nature are connected, are these two things connected? So one of the things he found out is like when there was a current flowing, he saw through a circuit. He saw the compass needles next to that circuit was getting deflected. Moment there was a current flowing, a compass needle would switch. Like it would not show a north, it would just flicker in the direction or opposite to like some direction would vary the moment the current would start flowing. Yeah. And stop. And then, so that's where the first idea comes into play, that electricity and magnetism are related to one another.
So, and then was there some kind of big gangbuster experiment that kind of definitely showed the two, or did this just kind of develop over time, these ideas that these two things were related?
No. So the idea of, as I said, the electricity and things like that was known to us in early Greek times, like 2,000 years ago. But in 1700s and 1800s, like we were starting to realize there is electricity, and you could pass electric current. Like one of the famous thing about like when they passed electric current, like to a frog's leg, it would twitch, kind of things. All those things were coming into play approximately late 1700s. But the actual scientific experiment started when we had Alexander Volta trying to created the first battery. I'm not going to get into that. That's a completely little bit out of the way of what I want to talk about. But so as we get the currents to flow from one into another, they started finding out in 1820, Ørsted, this philosopher, finds out that magnetism and current, electric current are related. This is 1820. By 50s and 60s, we have Maxwell, who pretty much within like 40, 50 years, we have working theory of electromagnetism with Maxwell is very well known for his 4 equations of electromagnetism that pretty much codifies everything.
And it all comes down to these electrons that are attracted or not, and the movement of electrons, right? And at what point did people start to think about this instead of some sort of like a force, and start to think about it in terms of a particle, and start to hypothesize that these are actually things that are flying around atoms? Is the concept of an atom, does it owe everything to this idea of electricity, or is it kind of the other way around?
So the idea of atom as an indivisible particle was known from chemistry. Like when chemical reactions and measuring like quantities of oxygen and hydrogen, you get a certain quantity of water. So they knew that like it always has to be mixed in certain ratios to give a certain quantity of water. Like 1:1 of hydrogen and oxygen would give me one unit of water, kind of thing. So they knew there was this indivisible unit that you could get it down to certain, and they called it atom. But they had no idea in 1800s that there was actually things called electrons. What we knew then started realizing with radioactive material, with the work of Marie Curie and other people, that atoms also are made out of subatomic particles like electrons, which have a negative charge and they carry current. Like people like Faraday and everybody, they did not know like what caused electricity. They knew electricity behaved in a certain manner, but they didn't know the existence of electrons.
Right.
If that's what the question you're getting.
Yeah. My I guess my follow-up would be then, at what point did they kind of get there where it stopped being some sort of unknowable force and a hypothetical to like who discovered the actual electron, that particle, or what?
So this particle was first the idea, the hypothetical particle was called electron, and it was done by this person called J. Johnston Stoney in 1874. And so this person said an idea is like there is this like unit of charged particle called electron. So this person comes in, but it has this idea, and this still comes out, but finally we came down to this famous experiment where we found out like this person called J.J. Thompson, who did this amazing experiment where he found out that something called a cathode ray tube. So where he found out the charge to ratio of an electron is constant, and it was independent of whatever cathode material are. So basically, what is this cathode ray tube or whatever? What is this? So cathode rays, it's basically what is happening. It's a glass tube, which is it's an evacuated glass tube, which means it is vacuum. So one end, what they do is and it is filled up with it has a very low density gas, because we cannot get a perfect vacuum. I would like to point that out. So then what is happening is then you would create like two ends with a positive end and a negative end. So then what they started showing is like started seeing is extremely very cool light beams going through. And
so this is like the first neon bar sign, basically. Right?
Neon bar sign that is happening, like that is happening
for I beer or one beer.
Yes.
I hope other people got that joke.
So that is what they started doing, and they started finding out that idea that when they reached and they were traveling, so they would do that, and they would have this electrons moving from one end to another. But what is interesting, what they did not really understand at that point what they were looking at. Now we know that those are basically energetic beams moving from one end to another, and so that's where the first idea comes into play of that, and it's little and that so the research started, and what they started finding out that this the particles that were moving would always have like the lowest ratio of their charge. They were always at a fixed ratio of what they were moving. They could measure their masses and the current. You could measure the current also, the amount of current they were producing, and they would know what is the charge over the mass ratio, and it was always a constant kind of. It never varied, no matter what element they ended up using to create or what gas used it.
What's that constant called?
There is a ratio of the charge of an electron divided by its mass.
But doesn't it have a name? What do they call that constant? Is that the Faraday constant?
It's E over M constant. So,
so it doesn't,
charge to mass.
It's
a
not
charge
a
to
Faraday constant.
mass ratio.
Okay. All right, I'd heard of a Faraday constant, and I thought that's what you were going to say it is. But so you can explain some more of this stuff to us when we get back from a quick word from our sponsors. We're the Science Nights in the morning.
All right, hello West Texas. We are back. We're the Science Nights, and today we're talking about electromagnets and electricity. And when we began, I kind of asked a really general couple of questions to Anirban. What is electricity and what is a magnet? Now I'm going to ask, what do they have to do with each other? So take it away, Anirban.
So, and we stopped about what? We talked about electricity at first, and one thing we need to focus on is we have been talking about how electricity and magnetism are related. There is one, however, very interesting thing which differentiates electricity and magnetism. So, if I have an electron which is negatively charged and sitting there, and I bring a proton close to it, they're going to attract each other because proton is positively charged and an electron is negatively charged. And if I put an electron there, it's going to repel each other, and because they have the same charge, so they're going to repel each other. Now, magnetism, interestingly, never comes into play if the electrons or whatever charged particle we have is not moving. So the electron or the charged particle that we are talking about needs to move for magnetism to, appear, if in lack of better words, for me to say, for it to show its effect, the magnetism, the electrons need to move. If it doesn't move, we are not going to have that magnetic effect that we look and feel in magnets.
So you're basically distinguishing magnetism from typical bonding that we see in compounds, right?
Yes. That's a very good way of putting it. Electrons, the ionic compounds, where you have one element negatively molecule or whatever slightly negatively charged and another molecule slightly positively charged, because they are two different charges and they're opposite charges, they attract and kind of create a compound in very layman's term. But that is not magnetism. That is not what is happening. Magnetism happening is in iron, for example, is the electrons that are in there that are moving around the nucleus of an atom. They're all oriented in a way that they're moving in the same direction, or for example, they're all moving in, let's say, clockwise direction. They're aligned, so they create this very strong attractive force in one direction and a repulsive force in the other direction.
Wow, that's really cool, because I never occurred to me, because I've taken chemistry and all that stuff, and you hear about protons being attracted to electrons, and that's why certain compounds form, but it never even crossed my mind that magnetism's different. It's all happening at once in one direction, and what the hell causes that?
Interesting question.
Very good. There you go.
And
we don't know, ladies and gentlemen. We're the Science Nights in the morning. We'll be covering it next week on what is it? Tell us.
So this is one of the very interesting ideas that we This is what we call an electromagnetic field theory. This is where the study of field theories comes into play, where we study how gravity works, how any force, fundamental force works in that level, is why electrons would repel each other because they have the same charge. Why do two same charges repel each other and opposite charges attract? So, and why does electrons, when they're moving in the same direction, creates this strong, or rotating in the same clockwise direction, when we align them, they are create a strong magnet, like an iron or something like that. How do we do that? So we don't actually have the idea yet how the field behaves in very well detail. Like, that is what you keep on asking the question why in science, right?
Yeah.
At a point comes, you have to just say, I don't know.
Oh, wow. So what I just asked you, you're saying we really don't know why magnets have all their electrons aligned the way that they do? We don't know?
I mean, that's a different question. Why magnets are aligned like electrons? Because that's
what I did.
Like
I asked what causes that, and that's slightly different. I grant you that.
So the question that you're asking, why they're aligned, because this is something to do with the energy levels. Because when like, say for example, like oxygen, like let's take oxygen, the thing that we breathe and everything, or has an atomic number of 8. What does that mean, atomic number? It means it has 8 protons in its nucleus, and which makes the nucleus have a charge of 8 units of positive charge. Along in that nucleus, it also has 8 neutrons in it, which are neutral. They do not have any charge. So what happens now, if I just take the nucleus of an oxygen atom, it is positively charged. Now, oxygen atom in itself is a neutral entity. So in order to balance that out, it has 8 electrons in it. Mm-hmm. Now, when you put the electrons all in there, all the electrons are now and this is at different distances, and they're spinning in certain way. They can spin in one up, they can spin on down, and they're all spinning. And way they spin is basically what they start doing. The electron starts filling up, is they will occupy the lowest possible energy level, because in the end, universe or any organism that we do, when it evolves, as you have seen, tries to use the minimum possible energy. Mm-hmm. That's the easiest. That's like one of the fundamental things we have.
Yep.
Just like that, electrons also wants to occupy in a position and be in a stable orbit around that nucleus in the lowest possible energy level. The second one comes in, it finds out what is the second most stable energy level. It will use that. And that's how the electrons get aligned the way they are spinning in certain directions, because their energy levels, that's what will govern them. And in certain elements like iron and nickel, their energy levels are in such a way the electrons are perfectly aligned in a certain direction, and they create that when they're spinning, and they create that perfect, like a very strong magnetic effect.
Does that have to do with the density of those substances, that the atoms or the molecules are so close together?
A little bit, but not. It's not really to do with density, because there are a lot of dense elements like gold and stuff, which is a lot higher atomic number than your iron and nickel. They are not as magnetic as iron and nickel. Mm-hmm. For example, so it's not that straightforward.
This is something we've probably talked about in a past episode, but for the listeners out there, we can't actually observe this going on, right? You can't look at little individual electrons, but one of the cool things about magnetism is you can actually observe magnetic fields, and you can see how the particles are kind of behaving, right?
Yeah, I mean, you can take a magnet, and what you can do is you put a strong magnet on top of, let's say, you take a piece of paper, and you have a strong magnet, like a horseshoe magnet underneath. And if you take iron, particles, like you can have iron dust and stuff like that, and if you put on the piece of paper and kind of shake it around, like, you will see the iron particles slowly kind of like taking the shape of the horseshoe magnet, right, which is basically what is the magnetic field. Mm-hmm. Or, for example, like if you put some kind of a fluid and you have iron particles in them, and you insert the magnet inside the fluid, you can see the iron particles kind of aligning themselves around like the magnetic field line. So you can do that experiment.
Or just go look at the cover art for the Metallica Death Magnetic album.
Absolutely, there is that too.
Admire that.
Well, that brings me to a quick question for you, Anirban. It's a one-word question. Polarity.
So polarity is basically the way it is spinning. So that's what it is. So if you are observing, so let's look at an electron. If you observe it spinning in a clockwise motion, you're going to see, let's say, a north pole. And if you observe it in an anti-clockwise direction, you're just going to see a south pole. That's what this is.
Right.
So it's the way the electrons are spinning. That's what it gives the rise to polarity.
So one thing, how does that relate to the two magnets that you can kind of make hover over each other? Because that's an experiment I used to do when I was a kid. We'd take two magnets and try to balance one on top. That they'd be about 2 to 3 inches apart, but one would be just hovering over it, and it would kind of give you a glimpse into what that magnetic field.
And you try to shove them together, and you couldn't
you
do
just
it.
Can't do it.
Holy cow, this is powerful.
Yeah.
Yeah. So basically, it's what you're happening, and the magnetic fields that we are talking about, which is resulting from the spinning of those electrons, they're either going to repel your magnet or they're going to attract it. Basically, is the same thing, like just much stronger.
Right.
That's what it is happening. It's just they are acting as if you have two charged particles which has the same charge, kind of thing. That's what they behave in that fashion.
Yeah.
That's what that is happening. It's just that the spinning and how they're spinning. So that's all that to is. It's to that.
And here just recently, we've been able to bridle that power with a new weapon, the rail gun, using magnets. Just recently, right?
I don't know much about the rail gun, so.
Well, yeah,
so
they basically use high velocity magnets they move magnets at a very high velocity to shoot bullets at an even greater velocity.
Something like that.
Something similar to that.
Which, we don't have awesome enough guns as it is. We need something.
No, we need to go through planets.
A bigger punch. Yeah. Just in case.
Yeah.
So you mentioned planets, Conley, and I'm going to segue here.
Okay, go ahead.
And Anirban, I don't know if you intended to talk about this, but so far we've talked about magnetism kind of on a really small scale. And I know we were going to try to connect it with electricity, but as a geologist, I have to talk about the Earth. So when it comes to the Earth, we're talking about a big magnet, right? We have our planet has its own magnetic field, and it's generated by our core. Do you want to tell folks how that works?
So we have a core, right? We have a solid iron nickel core. Correct me if I'm wrong, right?
That's the inner core is solid.
Is solid iron core, and surrounding it is we have a liquid or semi-liquid, right? Would it be semi-liquid? Yeah, right. A semi-liquid iron nickel core surrounding it. So both of them together creates our Earth's magnetic field, and it is very like I think you also know this, Thomas. Like you can also help me out here. It's not like very straightforward a north-south pole because the fluid part of the core is kind of spinning at a different way compared to the solid core, and that creates to a very complex magnetic field.
Yeah.
It's like a quadruple that we have on Earth, not just a dipole.
Yeah.
And those four put together create what we see. And yeah.
Yeah, and this is something we can actually observe too, right? I mean, in every textbook you pick up that's a geology or even a physics book, you see an illustration of the Earth and its magnetic poles and the magnetic field surrounding it. And at the North and South Pole, you can actually see that, the auroras, where you have the magnetic field interacting with solar particles, which is pretty cool.
And you can take a compass and it'll orient towards the magnetic North Pole. That's something anybody can do. Yeah, that's cool.
And that is one of the first things like people found out. They like this person called William Gilbert way back in 1600s actually proved this same thing. He took the compass And what he found out, the way the compass was inclined. So if anybody has taken a dry compass and like taken that out in the field and put it out there, they will notice how the needle is not actually flat. It's not perfectly horizontal. It's actually inclined a little bit to the plane. If you've taken a compass out there, and what he did was this amazing experiment. He took it to different parts of the Earth, and what he realized that that compass actually would change its dip. The dip would change. It would not be the same dip everywhere. It would kind of change all over. So what he realized is basically there is this magnet underneath which is creating that dip at different parts of the Earth depending on what latitude you are. And he said there is a huge magnet underneath our Earth's surface.
Yeah.
Is that the same reason why in that old the experiment that I'm sure all of us used to do is you take a needle, like a really fine needle, and you place it on top of water, and it just very, very barely just floats right on top of the water.
You have to rub it against.
Yeah, you have to rub it. Yeah, you rub it against it. You give it a little charge, right? And then it'll magnetically point north.
Yeah, and you can use that in case you don't have a compass, right? You can make like a makeshift compass. Yeah, that way.
And that is why, Conley, I exactly mentioned a dry compass. I did not mention like a wet compass, because in the dry compass, in the wet compass, you are not going to see the dip, because the dip that I'm saying, because in the like the compass that you are saying on the water, it's going to just stay flat with respect to the water. It's going to flow. It's going to be on the water surface, right?
Right.
But on a dry compass, the needle kind of like is inclined. It's like dips in towards the dial below. If you notice very carefully, it dips below.
A lot of people might not have. Most of the compasses you see for sale are wet ones. You see, it's got a little thing of water in it, but you can. Some of the older ones that are kind of nice would just be the needle's just kind of hovering there, and I guess that's what you're talking about with the dry compass. Yeah.
Yeah. So you take that and you'll see that the compass is kind of dipping. It's not like lying flat and moving around, hovering. It's actually dipping and hovering. Yeah. So if you take those compasses and go to different parts of the Earth, you will see that dip changing depending on what latitude you are on. And that is what William Gilbert did.
And watch out. I'll say, if you're out there using compasses a lot, probably nobody is because you're using your GPS, you're using your phone to navigate. But if you ever do use a compass, watch out of where you're actually using it and what you got near it. Yeah. Because like
belt buckle.
Yeah. Clipboards. A big steel shade structure, your iPhone. Just about anything can mess with a old-timey compass these days, so watch out when you use it, what you're doing.
And you have to take into account declination, too. That's a big mistake that a lot of people make is because the magnetic pole is at a slight angle to the geographic pole, you have to account for that with your compass by basically adjusting the scale on it.
Yeah, with a map.
But that's kind of going into too much detail.
Well, it is a good thing sometimes that it's so sensitive, because that's the beginning of each episode of Are You Afraid of the Dark, the Nickelodeon show. The kid would hold it too close to his belt buckle, the compass,
and then he gets lost.
Digging in the wrong place.
Yeah. You idiot, we're lost. And then the episode would start.
I'm sure there are 3 people out there who know that reference.
But there's more. But anyway, hey, we have just about a minute left, Anirban. Do you want to kind of segue into our next 10-minute segment with what you want to talk about?
I was just going to keep on going on this theme of magnets and throw in some historical tidbits along on the way, and if you have any more questions regarding the electricity and magnetism and electrons and all those and go over that. I did not really have a whole lot of things to in my mind. I just kept this as an idea, as a discussion.
Well, I for one, I can't wait for this. So we'll be right back after this, guys. It's Science Nice in the morning. Welcome back, everybody. Science Nights in the Morning here, and we're still continuing on this incredible topic of electromagnetism. And the one thing I remember from my rudimentary physics class, the one I was forced to take, which I thought was really incredible, is that pretty much all the electricity that we get boils down to kind of turning a turbine that is basically an electromagnet spinning. So hydroelectric power, how do you get from a river to electricity? You got to turn this turbine, and the turbine is an electromagnet. How does nuclear power result in that? Nuclear power creates a bunch of heat, creates a bunch of steam that turns a turbine. Steam turns a turbine. Coal burning power plants turn turbines, and all of it is based on that. So could you walk us through how exactly these electromagnets and these turbines give us electricity?
Okay, so remember what we talked about, that anything that if the electrons are moving, you can get magnetic field. Mm-hmm. And here's the thing, and what it means, the reverse is also true. Like that, if you can change the magnetic field, you can get electric current. So that's where this idea comes in. So if I can somehow, if the electric current is basically, if I can get an electric current moving, I can create a magnetic field. And therefore, the next step was to basically prove, if I can change the magnetic field, then if I can somehow change the magnetic field, can I get an electric current out of it? And that's what basically other people proved in Faraday and all these people in 1850s and 20s and Ampere and everybody went ahead and this bunch of experiments, and they showed that. Now, if I can move a magnet, and which means if I move a magnet closer, then the magnetic field is going to increase, right? The magnet strength is going to increase, and if I move it far away, then it's going to decrease. The strength of the attraction or repulsion is going to decrease. Now, if I can somehow make this thing move, make the magnet move back and forth, I can have an electric current being produced, which will vary, but it's still going to be produced. So that's what the idea was. Now, how do I make this magnet move? So I can sit around with a spindle with a magnet, and then I can have like a piece of wire, right? And I can move that hand crank it, and then I can get electric current. And that's what the first set of the turbines came into play as a demonstration. And remember Faraday, like when he was doing the demonstration of
with the prime minister.
Prime minister, that's what it is like. That's what the idea comes into play, is like, how do you do that? Now, the next step was basically trying to do that without us using that hand crank, is doing that. Then what we realized is where steam engine comes into play with James Watt and everything. We already knew steam. You could use steam to move things. Like that was like you could burn coal, heat water up, and you can get a steam engine moving. So that would the very rudiment idea of the steam engine comes into play. And once they realized that could be done, then they realized I could use the same principle and could get the magnet to move around in a circle.
Yeah, because they already had mills that would turn wheels for other things, and steam engines and things like that. Yeah. So then it was just a matter of you harnessing that power to spin a magnet around some wire, right? And that would create your current for you.
Current for you. So the first thing, they would need a directed, you would need like the first idea even before water mill, the water turbines or the hydroelectric power. They would already have the mechanism set up for the steam powered thing. So because we already had steamboats and steam engines, so you could get a very directional flow of steam. So they used that, and they could get the turbines or the windmills moving, basically to move, and there you have a current being produced. Very inefficient production if you're going to burn coal to get steam, but it was what we had at that time in plenty. So we used that. And then the next step came, we realized, well, there are these water that is falling down, and if I put the mill underneath that, just like in any other places, we could use falling water to harness electricity. So that's how That comes into play. The next, then we realize we have nuclear power, where you have the nuclear uranium basically decaying into lead and releasing electrons and atoms, which are moving out with extremely high speed, having a lot of energy, which if you put it in the water, this uranium, it heats up the water into steam.
That's what I always think is really funny, because I don't think a lot of people realize that that's all nuclear power does is create steam.
Yeah, they think there's this terribly polluting smoke that's coming out of the smokestack.
Yeah, it's steam.
It's just steam.
No,
yeah.
It's just steam that's coming out. And they do not produce any such carbon dioxide or methane or anything. What you're looking at, a nuclear power station that is coming out, that huge amount of gas is just steam.
Water vapor.
Water vapor. That's what
it is there is all kinds of nasty stuff that's a byproduct, but that's not what's coming out of that big stack.
No,
it's
that's
just steam.
that is not coming out. What is those nasty product is down below there. So that's a very different thing.
It's getting concentrated in these barrels and then sent over to New Mexico.
Salt mines.
Yeah, that's pretty crazy. And that's those electromagnets that are in those turbines. It all comes down to, just spinning it. If we could come up with ways of spinning that even more efficiently or with different fuels, then we could have electricity cheaper. But it all comes down to spinning that magnet. It's crazy.
Yeah, well, also, it actually... did you have something to say, Honorman? Go ahead. A response?
Oh, I was just going to say this, spinning this thing. Go ahead, Conley. I'll bring it in. I'll talk about that. Go ahead.
Okay. Yeah. I read an article a while back, and I just refreshed my memory that there is and this is an article published in The Guardian not too long ago, but there are companies out there that are starting to change. They've developed this foot pad that changes kinetic energy into electricity. And so what they're doing is these businesses, and I believe it started in New Zealand, according to the article, are basically lining their floors of their workplaces with all their employees with these pads. And as the employees move and work, they're actually paying for the light bill inside the building. So
cool.
They're translating the
No,
kinetic
man,
energy.
you know what's going to happen next? They're going to make us walk for electricity.
Slaves.
Yeah.
No. I thought it was actually pretty cool. It was something that is kind of cutting edge.
That's pretty cool
in electricity generation. So
and another cool thing, at home you can actually see one of these generators. You have one in your car probably, unless you have a car that's from like the 1920s. But correct me if I'm wrong, Honorbon, but the alternator in your car is basically a generator like this. You get your car started. It spins this magnet inside of your alternator, and that generates electricity that keeps your battery charged.
Battery charge, pretty much. Yeah, it's that what is happening there. Alternator and a generator. So, I mean, the motor is completely a little bit different, which takes the magnetic, which takes something else and converts it into power. But we're not getting that. But generator is the name generates. It's generating power. So it's generating electricity. That's what the name comes out of. So anytime you see generator, it means it's electricity that is being generated. So that's what it is. And when I was talking about that, it's not just that. You look at the windmills that are moving around, like in Texas, like in everywhere. That's the same thing. The windmills are moving around. It's not that the windmills is making something move, the magnet to move, spin. And that's what is creating the electricity. Another way of creating the power, I'm pretty sure most people are aware of this, is using tides to create that. Yeah. So as the tides move in, they spin the huge fins that are out there in the ocean, and they create this power basically. And as the tide moves out, again, it moves in the reverse direction. So that's another way people are using that principle, that changing the magnetic field can give us current or electricity.
Mm-hmm. So a lot of different ways of spinning magnets that we could potentially use now and in the future to generate electricity, right?
Mm-hmm. And I would like to point out, burning coal is the most inefficient of the lot.
Inefficient.
Yes, extremely inefficient of all these methods that I have gone over.
How about what if we boiled whale oil for electricity? Could we do that? And the steam created from burning up a bunch of whale oil.
That seems
Would that
efficient.
be good? That sounds real good. Yeah, that's kind of.
I should write a book about
I think
that.
that's like one blue whale should equal to like 1 billion years of electricity. I think it's a good investment.
Sounds like it, yeah. But yeah, that's something worth mentioning, that kind of we are generally going on a trend towards more efficient and more clean energy. And you know, when you think about the way we used to get power in the past, you know, by burning wood, right? And you used to burn wood to make a train move.
Right.
You know, that's crazy. And it's gotten better and better and better, and we've got some antiquated forms of electricity that are still around that, you know, will eventually go the way that wood burning trains went.
Because it's not efficient.
It's not efficient.
As simple. It's
dirty.
Not efficient.
It's dirty and it's not efficient.
Got to go with nuclear power.
If riding around in a horse carriage was efficient, we will still have horse carriages going around.
Right.
So it's, yeah.
Okay. Well, pretty nice. Now you're making me want to go on a horse carriage ride.
Yeah.
Here in Texas, man, I see them all the time.
Would be nice.
Out there riding their horses. They seem as happy as can be. And hey, I wouldn't mind trading the car in and taking a horse and having a little companionship.
I didn't know, Carly, you wanted to be an 18th century British gentleman with your horse carriage and your footmen
and some really hot calves.
You haven't seen Conley in a while. He's got a nice handlebar mustache and some mutton chops.
He's over here churning his own butter.
A rhinestone collar.
We're gonna have some scones with freshly churned butter here in a bit.
Carly, do you have like a monocle or something?
One monocle, yes, a monocle.
Yeah.
He's becoming really interested in India too for some reason.
Oh yeah,
yeah, for sure.
Empire. He keeps talking about Empire.
Does he have a flag?
No,
not yet.
Not yet.
Where he made this joke, like British conquered the world with the cunning use of a flag.
Right.
Yeah, that's how it works.
Yeah. No, I mean, like electricity and magnetism, it's like very nice. Like we keep on. There are a lot of things we know about electricity and magnetism, how they're related to one another. But what is always amazes me, deep down, if you keep on like probing deeper and deeper, and you keep me asking why electrons moving in a certain way create an attractive force, or why do spinning electrons create the force? Why not electrons which are at rest can't create that same magnetic force? That's a very interesting question, because we are trying to answer that, because we have a positive charge and electric charge, but there is nothing like a magnetic monopole. A magnet always comes as a dipole. It is always a north pole and a south pole together.
Well,
It is
cool.
never ever comes as a monopole.
We've discovered a fundamental mystery of the universe here, right here at this show, that is still unsolved. And so stay tuned for future episodes of the Science Nights in the Morning, and maybe one day we will solve this mystery.